let's look at the collision of 2 point masses. Here we have M2. Actually, let's make that M1. M1, M2, and then a collision happens and M2 gets scattered maybe like this, and M1 gets scattered as shown. Now the first thing you want to do is to set up a coordinate system, and you may want to set up something like this. That's my X and this is my Y component. Now this would be okay, but you notice that in this coordinate system all the initial velocities have components in the Y and the X and Y components, and also the final velocities will have components in the X and Y directions. So what if instead of doing that we put a coordinate system that looks more like this, where this is your X and this is your Y? Well, notice what happens then is that what we're doing is we're aligning the problem such that M1 is going basically in the X direction. So that's helpful. Not only that, actually let me draw this a little bit better because my X direction wasn't quite at 90 degrees. Maybe that's more like a 90-degree angle. Alright, so this is the X, this is the Y, and what I've done by putting that coordinate system in that orientation is made it such that M1 ends up being all in the X direction. So that's helpful. Now another thing that I can do is play, push play on the collision, and then you'd imagine that M2 moves in this direction and M1 is moving in this direction, and so then the collision happens, right? Alright, but what if I put my coordinate system not just in a convenient orientation but also with the origin traveling with M2? So in this case it is as if I'm riding on top of mass 2. And so if I do that, then this situation would actually look like this. I will have M2 here, but now because my coordinate system lies on top of M2, M2 would have 0 speed. It would just be stationary. And as we saw, M1 would then look as if it's just going straight along the x-axis. So now I've greatly simplified my problem because the initial velocity is all in the x direction, the initial momentum is all in the x direction, and it's all due to the momentum of mass 1. Now after the collision, I'll still have some scattering angles, so maybe M2 scatters out this way. and M1 scatters perhaps in that direction. Maybe something like that. Okay, so this will be the final states. M1 is now here, and M2 is here. And they have velocity components that I've drawn there. And so I'll go ahead and put the velocity components on top of them. Since there are vectors, I can take them and put them anywhere, so long as I don't change their size or their shape. So then the picture after the collision looks like M2 is here, with some velocity, and M1 is maybe here. It's hard to get it the exact same size that I drew it before. With some velocity component in some direction there. I'll make that a little bit larger so that some other drawings that I want to make will be easier to see. Alright. Okay, so now I have the before and the after pictures. And I can see then that each one of these will have a component in the X and the Y direction. So, for instance, M2 will have a component in the X direction and a component in the Y direction. In this case, it will be in the negative Y direction. And M1 will have something similar. Let's see if I can get an even lighter color. Okay, and these components are my final components of my speed in each direction. So now this is the picture I can work with, which is a much simpler picture. I will call this angle, let's see what color for angles. This angle will be theta, and this angle will be phi, which is the scattering angle. Okay, now I'm ready to put in my conservation of momentum equations. Which means that my momentum before the collision has to be equal to my momentum after the collision. Now the momentum before the collision, you see that it's all in the X direction, because all the initial velocity is in the X direction. So in the x direction, I have that my initial momentum is going to be m1, b1, 0. And that has to be equal to my momentum after the collision in that direction. So then that's going to be equal to m1, b1 final plus m2, v2 final. And in the y direction, my initial momentum is 0 because there is no momentum for mass 1 in the y direction, since it had no speed along the y-axis. So, and also m2 had 0 speed in this frame that I showed. So in the y direction, I have 0 is equal to my initial momentum, and that has to be equal to my final momentum, which is m1, b1 in the y direction final plus m2, v2 in the y direction final. Okay, now my conservation of energy equation is a scalar equation, because energy, kinetic energy, is 1/2 mv squared. So there is no x and y components there. It's basically the magnitude of the hypotenuse. So I will have that 1/2 m1 b1 initial squared has to be equal to 1/2 m1 b1 final squared plus 1/2 m2 v2 final squared. Okay, these are my equations 1, 2, and 3. Now I can go ahead and find what these components are, the x and the y components, after the collision, because I have my scattering angles. Alright, so for instance, for m1, I see that b1 final in the y direction has to be equal to b1 sine of phi. For instance, for b2 x final, that's going to be v2 cosine of theta, and so on. So I can rewrite my momentum equations with those terms. So let's do that. So I will have, for again, my conservation of momentum will be m1 b1 0, and here I could say cosine of some angle, but it's all along the x-axis, so that's just the magnitude of the speed is equal to the component in the x-axis. That's going to be equal to m1 b1 final times cosine of phi. Alright, that is this. Now we're going to do that portion. m2 b2 final times cosine of theta. Similar for the y components. Now for the y components, my initial momentum was 0. So then I have that m1 times b1yf, which is going to be v1y final, and to get the y component I just have to do the sine of phi. And for mass 2, m2 v2y final is going to be v2 final times sine of theta. Okay, now I want to be able to use these equations along my equation 3. So what I'm gonna have to do is square them so that I can add and cancel out all the components squared. Because you see now that I have just v2 final, v2 final, b1 final, b1 final. Alright, so I only have those variables now. I don't have all the ones that I had before, which were b2x final, b2y final, etc. Right? So I reduced my number of variables because I was able to put in the sines and the cosines from the scattering angles. And so I will have to combine my energy and momentum equation to find my solutions. Now, let's consider a case in which m1 and m2 are the same. We can also consider other cases in which m1 and m2 are drastically different, which will also give us some simplified equations. But in general, from this set of equations, you can find whatever you want. You just need to be given the actual masses and angles. But for now, let's go ahead and look at the case in which m1 equals to m2. And in this case, I can rewrite these equations and this equation in such a way that the masses are equal and therefore they will be canceling out. So for instance, for my momentum equations, I'll just have m b10 is equal to m b1 final cosine of phi plus m b2 final cosine of theta. Notice that I did not put any subscript on the masses because now all the masses are the same. So what I could do from here would be to factor out the m. So if I factor out the m, I would simply do something like this. M b10 is equal to m b1f cosine of phi plus b2f cosine of theta. And then I divide by the mass. And so I would get b10 is equal to b1 final cosine of phi plus b2 final cosine of theta. Right? So really what it ends up doing is all the masses end up being the same and equal, so they cancel out. You see the same thing would happen on the other equation. And even the same thing would happen in the conservation of energy momentum, because then that term would be equal to this term and equal to this term, so they would just cancel out. So I can go ahead and write all that directly, and I just cancel all the m's. And so my new equations are going to be, for conservation of energy, I'll have b10 squared is equal to b1 final squared plus v2 final squared. That's great. It kind of looks like a Pythagorean theorem. For the momentum conservations, I will put that one last, actually. I'll just move it down here. For this equation, I'll just write it without any masses. B10 is equal to B1 final cosine of phi plus V2 final cosine of theta. Alright, that's good. Let's put that there. And for this equation, the masses will cancel out, so then I would have 0 is equal to B1 final sine of phi plus V2 final sine of theta. And so these are now my equations 1, 2, and 3. I'll call this equation 1 prime. This will be equation 2 prime. This will be equation 3 prime. I'll copy and paste into the next page. And now let's work from there, and let's find our final velocities for mass 1 and mass 2. Okay, so I want to be able to use these equations with the energy equations. So what I would like to do then is to have it all in the same kind of quantity. So I'm going to try to find quantities that are V1 squareds rather than B1s to the first power, and so on for V2. So what I'm going to do is I'm going to square equations 1 prime and 2 prime. So then I will have B10 squared is equal to squaring that, which means I need to FOIL my terms. If you remember following, if you have A plus B and you square it, meaning you multiply times itself, you have then A times A is A squared, A times B is equal to AB, right? On the other side you have B times A will be equal to BA, and B times B will be equal to B squared. And so what you end up with is A squared plus 2AB plus B squared. So using that same process, I would get, for my equation 1, I'll get B1 final cosine phi squared plus 2 times the cross term plus 2 B1 f cosine phi V2 f cosine theta. Let's give myself some more working room. And then plus V2f cosine theta squared. Alright, same thing for equation 2. I'll have 0 squared is equal to 0 equals to B1 f squared sine squared of phi plus 2 B1 f sine of phi plus B2 f sine of theta plus V2 f squared sine squared of theta. Those are now my equations 1 and 2, and my equation 3 is still the same. It's already squared, so I'm just going to rewrite it. B10 squared is equal to b1 final squared plus b2 final squared. So that's a good set of equations. Now what I'm going to do is I'm going to add equation 1 and equation 2. I guess this will be double primes now, but I'll add those two equations. And what that's going to give me is I'm going to be able to have terms like this added together, and you notice that I'm going to get a cosine squared plus a sine squared, which is your Pythagorean theorem identity. Sine squared plus cosine squared of the same angle would be equal to 1. So I'm going to do that, and just to make room, I'll erase that for now. So now I'm going to add these two equations. I'll give them names. This will be equation 1 double prime, equation 2 double prime, and so I'm going to add 1 double prime plus 2 double prime. Alright, let's see if that should be enough space. Okay, so I add this b1 0 squared. I add these terms, b1 final squared times sine squared of phi times cosine squared of phi. I add the middle terms, I put a plus sign that wasn't going, shouldn't be there. Alright, so now I'm gonna add these two together. The middle terms. I'm going to notice that this is the same as that, and this is the same as that. So I have 2 times b1f sine of phi plus cosine of phi plus let's not close that parenthesis just yet, plus b2f well, let me just add them together and then I'll do the cancellations. It'll be easier to see where I'm going. Okay. 2 b1f cosine of phi v2f cosine of theta plus 2 b1f sine of phi v2f cosine of theta. Okay, and now I'm going to add the last terms. Which is going to be b2f squared times cosine squared plus sine squared of theta. Alright, well, as promised, this is equal to 1 and that is equal to 1. So let's write those down. b10 squared is equal to b1 final squared times 1 plus b2 final squared. Right? And now I have this little mess here. Now, notice that I have a lot of common items. 2b1f, b2f, 2b1f, b2f. So let's put those together. And now I put all the cosines and sines. Cosine phi, cosine theta, plus sine phi, sine theta. Okay. Now, this is my equation 1 plus 2. Right, or I guess really it's 1 double prime plus 2 double prime. I just simplify that. Let's call that equation, what should we call it? I don't know. Call it equation 4. And now let's write down equation 1 again. Equation 3. So equation 3 said b1 0 squared is equal to b1 final squared plus b2 final squared. So you notice something very interesting. Equation 3 prime is exactly that. And so the only way that you can have equation 4 and equation 3 be true is that if this is equal to 0. In other words, if you had an equation like this, 3 is equal to 3 plus a, well then you know that that would be the case. Alright, so if I put in this equation in here, I would end up with b10 squared is equal to b10 squared, because those are the same things, plus this whole mess right here, 2b1f, b2f, cosine of phi, cosine of theta, plus sine of phi, sine of theta. Alright, so then these two have to cancel out, and so I get that 0 is equal to 2b1f, b2f times this mess. But if you remember your angle identities, your angle sum identities, you would recall that this portion of the equation is simply an angle addition formula, which is cosine of phi plus theta. That's it. Now, you know that b1f and b2f are not gonna be 0. The collision's not gonna happen and then and then the particles are just not gonna move, right? They'll have some speed. So this cannot be 0. This is something. So then this has to be 0. So then what you have is that cosine of phi plus theta has to be equal to 0. And if you remember the graph of cosine, it'll look something like this. It's 0 for pi over 2, which is also 90 degrees. And so our result is that for the cases where masses are the same, we always have that the scattering angle of one mass plus the scattering angle of the other mass is going to be 90 degrees.